All right, all in all, really good stuff. Really liked what I was seeing from people. So let's start with our example A here. So trying to figure out, this is again, a very classic example that shows up a ton. But if we're thinking about the arrangements for the letters in the word Mississippi. First and foremost, thinking about the number of objects that we are trying to line up. What is the total number of objects that we are trying to kind of sequence here? So we've got 11 total. And so ignoring the possibility for overlap, ignoring the possibility for not caring about certain orders, how many total ways do we have to just line up 11 objects? Perfect. This is going to be 11 factorial is like our big, large counting sample space that we are going to need to make smaller. Why do we need to make it smaller here? Where do we see the potential for not caring about order? Okay, so we've got these 4 I's. We've got these 4 S's. And we've got 2 P's here. And so we should be able to shuffle around the I's in any way that we want. We should be able to shuffle around the P's in any way that we want. We should be able to shuffle around the S's in any way that we want. How many ways can I shuffle 4 spaces if each space has an I in it? 4 factorial. And so what do I do with my order if I want to get rid of that order kind of being factored into this 11 factorial? Divide out an initial 4 factorial. We'll say that this 4 factorial is the order of the I's specifically. But it wasn't just the I's that were creating a problem. We also want to be able to shuffle the S's. So how much order am I going to have to divide out in order to account for the S's? Also 4 factorial. And then to take into account the order of the P's, what am I going to have to do? Divide out 2 factorial for the order of the P's. Technically speaking, it is maybe a little bit more precise to include a 1 factorial here as well. What would the 1 factorial stand for? It would stand for M. It's like the number of ways that I could shuffle M around. There's only 1, right? I can't switch M with any of the other letters. It's going to be unique. And so the number of ways that I can shuffle 1 space is just by leaving it alone, by just not doing anything to it. And that would give me what I could do with each letter. Similarly, for the examples that we were looking at yesterday, maybe here having a 1 factorial to stand for the A's that I could shuffle and a 1 factorial to stand for the S's would be quote unquote better. But just this idea of we're dividing it out. And if you include those 1 factorials, interestingly, the total of all the numbers that you add, so for instance here, the 4 plus 4 plus 2 plus that M plus that 1 would equal 11, the 11 objects that we are working with shuffling here, which is kind of cool. All right. B was, I thought, a little bit tricky. I tried to make it a little bit tricky. Although people generally did really well, which is good. The main thing about B is that this is very much kind of a hidden either permutation problem or combination problem. So either this is selection where we care about order, or this is selection where we don't care about order. And here, it's really, really important that we understand what we mean by like caring about order or not caring about order. What would it mean for us to want to care about order for something like this? And essentially, for a coin tossing event, this would have to do with caring about the order in which the coins were observed. So for instance, let's say we toss 50 coins and coin 17 turns out to be heads. And we can do this, right? We can set up our diagram where we have like 35 slots as heads, and we have 15 slots as tails. And we look at the various coins and we say, okay, coin 17 goes into the first slot for tails or goes into the first slot for heads or whatever. So for instance, maybe coin 17 goes here. And maybe then we look at coin 52, or 52 wouldn't exist, coin 48. Coin 48 also is heads, so coin 48 would be here. If I had instead looked at coin 48 first, and then had looked at coin 17, have I done anything to change the arrangement of coins? No. Should that necessarily get me a different, unique setup? Is that its own unique output? Definitely not. And so what matters here in terms of order is that we don't care about the order in which the coins are counted as being heads or tails. What does matter is that coin 1 landed heads, right? That's the only piece of information that matters. If coin 1 had instead landed tails and a different coin that had originally landed tails landed heads, that's a new way to arrange 35 heads and 15 tails. And so in this case, this is a combination. We don't care about the order in which we mark the coins as having landed heads or having landed tails. And so for our combination, how many objects are we lining up? How many coins are being tossed? 50. We have 50 factorial ways to line these up. How many ways do I not care about because I don't care about the order in which I note that the coins landed heads? What do I have to divide out to say I don't care about the order for coins that are heads? 35 factorial. And what do I have to divide out to say that I also don't care about the order of coins that turned out to be tails as well? Also have to divide out a 15 factorial because it's not important that coin 7 landed tails and coin 8 landed tails. That's the same as saying that coin 8 landed tails and coin 7 landed tails. So it's whatever. 50, choose 35. Couple of things to note here. This is slightly different in terms of our setup of thinking about like choosing something. There isn't like a being chosen or not being chosen. But what we do have is being sorted into two binary categories where we are either landing heads or we are landing B. And that is effectively the same as being sorted into a bucket for chosen and a bucket for not chosen. Mathematically, it's the same. Right? If I said pick up all of the coins that landed heads, okay, all of a sudden we actually are making a selection in terms of our heads or our tails, things like that. But this idea of choosing doesn't necessarily mean we are literally choosing. It could mean that we have found the number of ways that an object can be, or a set of objects can land on one of two binary options. What we see with the lettering is what happens when there are more than two buckets. For instance, we have a bucket for what happens when we are M, a bucket for I's, a bucket for S's, and a bucket for P's. And the different buckets have different like ordering principles to each one, and you have to adjust for each of those buckets, which is why we divide out the ordering from each one. All right, questions here with our bell work? All right. What we are going to be doing is really kind of similar to taking this coin analogy and applying our idea of choosing with it. We're going to be doing that with a fairly seemingly very disparate field of math. So this is kind of the pre-cal tie-in for this combinatorics stuff. What we are going to be considering today are called binomial expansions. So binomial, that's just going to be some kind of a plus b. And we are saying we are taking a binomial and we are raising it to some kind of power. And the goal is to be able to say what this is going to look like. Now, importantly, this is not going to look like a to the power of n plus b to the power of n, because we don't want to give our teacher an aneurysm. And so we are not going to distribute an exponent through addition, because we can't do that, because that's banned and you will go to math jail. And also it will give me a massive headache and I will probably cry. So don't distribute the n through the addition. It will make me very unhappy. You don't want me unhappy when I'm grading your quizzes. What we would normally do instead, unfortunately, is a lot worse. It would be nice if we could distribute the n through. We cannot. But what we have to do instead is we have to write this out as like a plus b times a plus b times a plus b times a plus b, however many times. And then we like multiply them all together, either using foiling or using our Punnett squares or whatever methodology that we have. And if n was like 50, that would be the worst thing in the world, unimaginably cruel for me to ask anyone to do that. But even for relatively small n's, like when n is like 6 or 7 or 8, this would still not be a particularly pleasant process. This is not going to be very fun to try and brute force. So what we're going to be looking at today is a way to derive elements of that expansion using some of our combinatorics knowledge. The A's and the B's, in particular, the powers of the A and the powers of the B, those aren't too horrible. If we think about this expansion, we know that this is going to be something times A to the power of 8, B to the power of 0, plus something times A to the power of 7, B to the power of 1, plus something, if this is, I guess, if this is 8, we're running with this being 8. Something times a to the power of 6, b to the power of 2, and so on. And so really the only piece of information here that we are missing is what goes in these blanks, what goes in these somethings. Well, it's going to be a coefficient, and that's what we're going to try and figure out. And I'm going to give it to you, what this is going to look like, and then we're going to see actually where this comes from. So the coefficients that go inside each of these blanks can all be written in the form, I'm going to refer to them as, we'll say, the coefficient for our terms, which I will say is k sub r can be written as n factorial over r factorial times n minus r factorial. Which is to say that every single term in our expansion can be written as this n factorial over r factorial times n minus r factorial times a to the power of r, or a to the power of, realistically, it's a to the power of n minus r is generally how you're going to see this, times b to the power of r. Okay, so what's going on here? The first thing, and this should be fairly surprising, this should not be obvious, is that the coefficients for this expansion are somehow related to the combination formula that we looked at yesterday. So somehow the coefficients for a particular a to some power, b to some power from this particular expansion are mathematically equivalent to picking 3 representatives from a class of 20, or picking figuring out the number of times that a coin toss is going to land on heads, number of ways that a coin is going to land on heads if it's going to land on it 35 times out of 50. Okay, so what we're going to do is we're going to explore a little bit why this actually makes a little bit more sense than it maybe seemed. We're going to see how we can kind of use this in a really, really nice way. It ends up being fairly efficient, which is nice. We're going to start with a couple of concrete examples, and then we'll look at a different way that we could arrive at the same information that is debatably easier. I don't know if easier is necessarily the word that I would use, but similar. And so for our example, we're going to start with a relatively small case. We're going to look at what happens when we take a plus b squared. Okay, a plus b squared is not a squared plus b squared. It is instead a plus b times a plus b. And normally, when we would do this, we either have like a formula that we have memorized, or we would FOIL this, or we would use the Punnett square method, and all of those are perfectly fine. There's nothing wrong with any of those. I am instead, though, going to use what I might describe as the kind of true distribution way to go about doing this. The way we're going to think about this distribution, we've got these 2 objects that are being multiplied together. We've got a plus b being multiplied by another a plus b, and we can imagine this being one giant chain. And this a plus b, this first a plus b object, has a choice. It can either donate an a, give an a, multiply an a, or it could multiply a b. And the way that this distribution works is it does both. We're going to take the sum of what would happen if it multiplied by an a and what would happen if it multiplied by a b. And so this is equivalent to looking at a times a plus b, where this a is coming from our first object's a. So if our first object donates an a, and we are adding that to what happens if we get b times a plus b, where if object donates a, b. Okay, now this is just distribution. That's not too bad. From our first set here on the left, A times A gives us, well, that's just going to, I'm going to leave this for now as A times A. A times B is going to give us A times B. We'll worry about that here in a moment. So that's all coming from what would happen if the first object gave an A, and then our second set here, which we're going to look at these red brackets. If our second object gives us an A, we'll end up with a B times A. And if our second object gives us a B, we'll end up with a B times B. All right, adding all of these together. I'm only using the brackets. They're not doing anything functionally. I'm just using it to kind of show you what is becoming what, like which piece I am matching to which. So they're not very functional, but more there to make it clear what is happening, or a little bit more clear. Any like terms that we can combine? We've got the two AB terms that we can add. And so our final expansion here should be of the form A squared plus, we've got AB plus BA, but BA and AB are equivalent because of what property? Commutative property we said yesterday. So that we've got two ABs and we've got one B squared. And the question is, where did this 2 come from? AB plus AB. Yes, they're somehow like maybe connected to coefficients, which is an idea that we're going to examine after this. But we could really think of the ABs that we combined as being like every single possible way that we could make an object that has exactly one A and exactly one B. One way that we could do that is having our first object donate an A and the second object donating a B. And the other way we could do that is having our first object donate a B and the second object donating an A. And there are only 2 ways that we can do that. And so we get 2 ABs. Conversely, the ones, or not conversely, similarly, the ones come from the fact that there is exactly one way to get a string of all A's. The only way to do that is for every single object along the way to have given us an A. Likewise, there is only one way to get all B's. It requires every single object along the way to give a B. So there's no flexibility in how that A squared or that B squared came from, but we saw 2 different ways to arrive at this AB term. And so really these coefficients represent the number of ways to make a product with one A and one B. Now let's ask an ordering question, just really quickly. Would I have gotten a different result if I first looked at what the second A plus B object was going to donate, rather than first looking at what my first A plus B was going to donate? No. Right, we get the exact same result if we start by looking at the second versus starting by looking at the first. And so does the order in which these donations or these assignments to being A or being B, does that order matter for our ultimate kind of goal here? No, it gives us the same result regardless, kind of similar to the coin tosses. Doesn't matter whether I'm looking at coin 17 first or looking at coin 6. I could shuffle that. That'd be totally fine. What matters is what coin 17 says and what coin 6 says. In this case, all that matters is that for our first AB, it came from the first object being A and the second object being B. And for our second AB, it came from the reverse. It didn't matter the order in which I considered those. All right, let's scale up a little bit. Let's consider A plus B cubed. We're going to find something very similar. Again, this is not A cubed plus B cubed. This is instead A plus B times A plus B times A plus B. Okay, we're going to do something similar. Again, does it matter which object that I start with for figuring out the donations? No, order shouldn't matter here. I should be able to start with any of them. So I'm just going to start with the first one, and you could assume that you'd get the same result from starting with any of them. You can confirm that if you'd like. You'd have to like put little trackers on each of the A's and the B's to make sure that we're getting the same combinations of them, but we would. Take my word for it. Or don't take my word for it and do that. That'd be totally fine. So exact same process. First object is going to donate an A, and it's then going to donate a B. We're going to take the sum of those. So this is equal to A times A plus B times A plus B plus B times A plus B times A plus B. Now we're going to look at the possibilities for what the second object is capable of donating. All right. So second object also can either be an A or a B. So if we set our first object, we'll say go ahead that is going to be an A, then we get either A times A plus B. That's if both the first and the second are A's. And we also get A times B times A plus B. And likewise, if the first is a B, we either get B times A plus B, or B times A plus B. Which, coming from this piece here. And lastly, our third object is also capable of being either an A or a B. And so we get, if the third object is, say, an A, we get that this is A times A times A from this first one. If the third object is a B, then A times B. This is analogous to what we have here. If our third object for our second piece here is an A, we get A times B times A, and we get A times B if it's a B. All right, we get plus B times A plus B times A times B. Next, that's this one, the same as what we have here. And lastly, we get B times A and B times B here. All right. Anything that we can condense? Any like terms? I guess one question, again, kind of important. Is there a difference here between A times B and A times B times A? No. So what we really care about here are just the number of objects that have given us an A and the number of objects that have given us a B. That'll tell us whether or not they match, whether they line up. How many ways can we get 3 A's and 0 B's? Say again? Yeah, just A times A times A. There's only one way to do it, and it's if every object donates an A. So that would be 3 A's and 0 B's. You generally don't write the B to the 0. I'm including it here just so that we can kind of see number of A's, number of B's. How many different ways do we have that we can have 2 A's and 1 B? So we've got one here, we've got one here, and there's one more actually. Just right here. 2 A's, 1 B. For a total of 3 ways to get A squared B to the 1. Again, you generally wouldn't write the 1. I'm doing it to include that we know number of A's, number of B's. How many ways can I make 1A, 2 B's? Perfect. That is another 3. And then how many ways can I do 3 B's and 0 A's? 1. And we'll include, we've got 1 with 0 A's and 3 B's. And so this process of multiplying out this binomial is effectively the same as running through every single way that our objects can either give us an A or give us a B. These coefficients that we get are the sum of the ways to end up with these particular combinations. In this particular case, if we have 3 objects that are either giving us A's or giving us B's, and we don't care about the order in which we receive those A's and B's, which we have said that we do not, then there are, well, 3 objects would be 3 factorial different assignments. We would divide that by 2 factorial times 1 factorial, 2 factorial to say that we don't care about the order in which we receive the A's, and 1 factorial to say that we don't care about the order in which we receive the B's either. And so this process, again, of multiplying out these binomials is remarkably enough the exact same as a combinatorics problem. And we get that this coefficient is, again, this 3 factorial over 2 factorial, 1 factorial, where this is our number of A's, and this is our number of B's. And it works out that this is 3. Cool. All right, questions here with our kind of origins of our coefficients. Yeah, Dylan. Exactly. Depending on, so yeah, this is a good question. So each term, on top of having the number of A's and the number of B's, think of that coefficient as telling us the number of ways that we can get that specific arrangement of A's and that specific arrangement of B's. So we would get a different number of ways to get 3 A's and 15 B's than we would if we wanted 9 A's and 9 B's. There are different numbers of ways to do each one. And so each one will give a different combinatorics problem. And what you have kind of identified is that if we were asked to do the full expansion using just this would still not be particularly pleasant. It's not too bad, but it's not great. And we could like look at that. So for instance, if we wanted to do a plus b to the power of, let's do 4. Let's do a relatively small, or we could do like 5 or something like that. Then we order this. Our terms are always going to fall into the order of we start with what happens when we have all A's, and we work our way down to what happens when we have all B's. So we're going to start with 4 A's and 0 B's. And then we're going to subtract 1 from the A's, add 1 to the B's each time we move to get until we only have all B's. So this is going to look like something times having all A's and no B's plus something times having 3 A's and 1 B plus something times having 2 A's and 2 B's plus something times having 1 A and 3 B's plus something times having 0 A's and 4 B's. And what that something is a different choose equation, or not choose equation, but choose value depending on the number of A's and the number of B's. So for instance, here we would have 4 factorial over, well, we want to get rid of the order in which we look at the A's. So 4 factorial and 0 factorial. What is 0 factorial? 1, so we're not dividing by 0 here, so we're okay. For this one, we would be looking at like 4 factorial over 3 factorial, 1 factorial. Here would be like 4 factorial over 2 factorial, 2 factorial. This one would be 4 factorial over 1 factorial, 3 factorial. And then this one would be 4 factorial over 0 factorial, 4 factorial. Where in the denominator, the number on the left, that 2, tells us that we have 2 A's. And the one on the right tells us that we have that many B's. Numerator is always going to match the exponent. Yep. Well, exponent factorial, yeah. Yeah. So this is just no, this is not how we're going to do this, but it is an option that we have for being able to do this. So what we're going to find is that this is, again, it's not horrible to do. Like, this isn't terrible. It's a little bit unpleasant, especially if like I asked you to simplify, which I'm not going to. But like if I did, this could be a little bit unpleasant. And we could imagine it being a little bit, again, annoying to do this. Not too bad, though. We are going to look at another way to do the full expansions. What we are going to use this for more is going to be as a way to kind of extract specific term information, because the other way is not going to be well equipped to doing that. The other way is going to be really, really nice for doing these smaller values of n and fully expanding them. And our binomial can do that, but it can do really, really well taking a large value of n and just plucking from that what a particular term is going to look like. So we'll have some options here with what we can do. So for instance, and my sequencing was a little bit out of order here, my bad. We're going to start with example 2, and then we're going to work our way back to example 1. So in this case, we were trying to figure out the requested term from the expansion of the given binomials. Starting with A, we're trying to find the 4th term for this particular binomial. What I would do, just kind of leading off here, what is our value of A and what is our value of B? Yep, perfect. Just to be like really, really clear, we want to make sure we're raising -3 to our power, which will be significant in that, like, for even powers, it would become positive, and for odd powers, it would stay negative. So just kind of making a mental note that we are raising all of -3 to these various powers, and all of, in this case, y, but you could imagine like 2y to these various powers. All right, we need to figure out what the fourth term is going to look like. We need to know the number of a's that the fourth term is going to have, and we need to know the number of b's that the fourth term is going to have. It'd be tempting to say, oh, it's going to be 4, but it's not quite that simple. It's almost that simple. It's not quite that simple, though. My recommendation is just to start counting the number of b's. Our terms are always going to follow this sequence that we see here, where we start with 0 b's and we just slowly work our way up as we go term by term, adding to the number of b's that we get. This would be my advice. Start with 0 for b's and just count your way up. If I start with 0 b's, so first term is going to have 8 a's and 0 b's. Second term is going to have 7 a's and 1 b. Third term is going to have 6 a's and 2 b's. And my fourth term is going to have 5 a's and 3 b's. This is going to look like something times a to the 5th b cubed. Which we could have kind of done with process of elimination. I wouldn't be trying to keep track of the a's and the b's when I'm doing this. I would count the b's. I would say we start at 0, first term 0, second term would be 1, then third term would be 2, fourth term would be 3. So I'll have 3 b's. I have 8 objects total. If 3 of them are giving me b's, how many must be giving me a's? 5. That's where the 5 would come from. So notice that the exponents here always add to be 8 because we have 8 objects total giving us either an A or a B. In this case, 5 of them giving us A's and 3 of them giving us B's are basically equivalent statements. You only need to know one and you can very easily figure out the other. All right, fantastic. We have a scenario in which 5 of our objects are being sorted into bucket A, 3 of our objects are being sorted into bucket B. We don't care about the order in which they go into either bucket. What is our coefficient going to look like? How many objects total are we lining up? 8 objects total. How many ways do we have to do that? 8 factorial. And then what do I have to divide out because I don't care about order? 5 factorial because I don't care about the A's, and 3 factorial because I don't care about the B's. I mean, I don't care about the order in which I get those A's and the order in which I get those B's. This is generic. We have specific values of A and B. Okay, so we'll plug in those specific values of A and B, then we'll be done. This is going to be the same as 8 factorial over 5 factorial, 3 factorial. A we said was y, so y to the power of 5, and B we said was -3, so -3 to the power of 3. And you could figure out what that is. I think it ends up being 56. You could plug that into your calculator. Math, probability, NCR, N would be 8. R could either be 5 or 3. Funny enough, this is symmetric, which we would find not too difficultly. And then multiplying that by -27, that's fine and all. I don't require you to simplify. Box your answer. Call it a day. All right, questions here for example 2A. So I would start by figuring out the number of B's, which is the easiest to start with. Start at 0, count your way up. And then use that to figure out the number of A's, and then you're setting up the coefficient and plugging in the A's and the B's. All that. Take a minute, we'll say maybe 5-10 minutes. Figure out what the 7th term for B is going to look like. Figure out what the 10th or 9th term for C. I would just as this is like nitpicky, but just to make sure it's clear that there's 3 against the negative, I would always leave those in parentheses. And it's going to be a similar comment to like what I do with the 2y and what I do with the 4x, things like that. Just making sure they're in parentheses so it's clear that it's getting targeted by the powers. Perfect. Looks great. Perfect. How many B's are we going to end up with? We start at 0. We want to count 7 spaces. How many B's are we going to end up with? That looks really good. Very nice. This looks perfect. The only thing that I would just adjust ever so slightly, just to make sure that we're being really, really clear about what this exponent is hitting. Here, I would put parentheses around this, just so it's clear that the 6 hits the 2 as well, that it's seeing the 2. But otherwise, it's perfect. Yeah, that's great. Very, very nice. Coefficient looks great, and then it's just plug in the specific values of whatever A and whatever B. So if we start counting up from 0, and we want to move 7 spaces, how much is 0 going to, what is 0 going to turn into by the time we get to the 7th space? So starting at 0, so first term would be 0 B's, then 1, then 2, then 3, then 4, then 5, then 6. So it's all, so B is always 1 less than the number of term, basically. And A is going to be, is just that minus whatever N is, N minus M. Perfect. Looks great. All right, overall looks really, really good. Very happy with what I saw. For B here, what are our values of A and B? X and 2y. Just kind of things to note for what we've got going on here. How many A's and how many B's did we find that we would have by the 7th term? 4 A's and 6 B's. Very, very good. So counting up 0, 1, 2, 3, 4, 5. By the time you get to the 7th spot, you would have 6 B's. And then if we have 6 objects that are donating a B, then the other 4 must be donating an A. It's that binary that we've got there. 10 objects total. 10 factorial to represent the total number of ways that I can line up 10 objects. We want to divide out the order from the A's. We want to divide out the order from the B's. And we said that A was X, A to the 4th, and 2Y. Notice how I'm using the parentheses here to the power of 6, just to make it really clear that the 2 is getting tagged by the 6, just to make it clear. Right, for the 9th term of the for C, of what we are given, how many A's, how many B's? 4 A's and 8 B's. Very, very good. We've got 12 factorial total possible orderings. We want to divide out 4 factorial for the number of A's, 8 factorial for the number of B's. A is 4x. Or said we have 4 of those, and B is -5. We said we have 8 of those. And we'll go ahead and add here. Binomial coefficients, this was our for k sub r a to the n minus r b to the r, k sub r is equal to n factorial over n minus r factorial r factorial. N minus r. Yeah. Which is the, if r is basically the number of b's, kind of. And you can put the r and the n minus r on either one. It doesn't matter. These are symmetric, which is, we're going to visually see that here in a second. And so it doesn't really matter whether r is referring to the number of a's or whether r is referring to the number of b's. N minus r just says the other ones. So if we have r a's, then we have n minus r, all the leftovers. We have that many b's. Or you could reverse those and you would get the exact same thing. Yeah, Dylan.
They prefer the 10th term within the A1 B9, then when would be 10?
When a is 0. So that would be when we have no a's, when all of our objects, when all 10 of our objects donate a b and none of them donate a's.
What term would that be?
That would be the 11th term. So you have one more term than your power, basically. Yeah, for all of these, you'll notice that we have one more term than our power. And that's exactly why, is because we have, if we have a power of like 10, then we have 11 different possible ways that we can donate A's or not donate A's. And we have, the lowest would be donating 0 and the highest would be donating 10. And so there are 11 total stops along the way, basically, for that. Which is why notice the term number and the powers that we're looking at are a little bit offset. That's why that's happening. Good question. Other questions here? I think this is kind of crazy. I think that it's very strange that a counting problem that you often see associated with like filling in the number of seats in a classroom, or polling a population, things like that could then carry over into something as abstractly mathematical as figure out the coefficient that sits in front of the a squared b cubed term in a binomial expansion. And those are the same problem is pretty cool. And hopefully we, at the very least, get, if not a full understanding of why, at least it feels maybe a little bit tangible as to why that would be the case. All right, let's take a look at our second way. So we kind of already addressed in what we had looked at before that this is a really cool, pretty powerful tool. And it's not horrible to do the full expansion like this, but it's a little horrible to do the full expansion like this. It's not like terrible, but there are other maybe debatably easier ways that we can arrive at the same result. So let's go back to thinking about this a plus b cubed object. And this time, rather than thinking about it as a plus b times a plus b times a plus b, let's think of it as acting on a change that we make to something that we already know. In particular, this is going to be a plus b times a plus b squared, where we already figured out the expansion for a plus b. Already, we should hopefully feel why this only is going to be convenient for small values of n. Notice that the knowledge that we need in the setup requires us to know about the expansion that came before. This is a very recursive process, and recursion is fine for small values of recursion, and it really gets quite horrible very quickly for large values of recursion. So for instance, if I wanted to try this for a plus b to the 10th, then I would need to know what a plus b to the 9th is. If I wanted to know what a plus b to the 9th is, I would need to know what a plus b to the 8th is, so on. So this process is one that is going to be nice for relatively small values of n, but when n gets up to like 50 or 70 or 100 or something like that, not going to be particularly pleasant. But again, this is more to be demonstrative than anything else. We know that this should be equal to a plus b times a squared plus 2ab plus b squared. And doing what we were doing before, that object that we're multiplying our a plus b squared by is either going to give an a or it's going to give a b. So if it gives an a, then this is a times a squared plus 2ab plus b squared. And if it gives a b, then this is going to be b times a squared plus 2ab plus b squared. Distributing, this gives us a cubed plus 2a squared b plus ab squared plus ab squared, or sorry, a squared b times a squared b plus 2ab squared plus b cubed. All right. As far as like terms go, what do we have that we can combine here? Okay, we've got this a squared. So we've got the ab squared and the 2ab squared. So we've got this and we've got this. Those can certainly be combined. And we've got exactly the 2a squared b and the a squared b here. For a total of 1 a cubed. Again, only one way to make a cubed. All of the things are donating a's. We have a total of 3 a squared b's. We have a total of 3 ab squareds, and we have only one way, again, to make this b cubed. So again, my question is, where did these 3's come from? And this one's a little bit interesting. I want to make the observation that they came from, obviously, combining these like terms. But then when we consider where did the like terms come from, we get something interesting. In particular, notice that this 3a squared b, the second term that we got, was taking the middle term from our multiplying everything by a and adding it to the first term of multiplying everything by b. Likewise, our 2a or the 3ab squared, again, the 1b squared, this initial ab squared, came from taking the last term and multiplying it by a and adding that to the middle term and multiplying it by b. So we should be able to use the coefficients of the previous term to in some way derive what the coefficients of the subsequent term should be. We've got this kind of like weird diagonal addition something or other going on here. And so we should be able to parse out what that is actually going to look like. In this case, the A, B's, think of the number of A's, the number of B's as telling us more about like where in our expansion these are going to end up. Like, are they going to be the first term, the second term, whatever, how many A's or how many B's are associated with that. If we want to strip down to just the essential information, then we are going to just care about the coefficients. So we're trying to make some kind of statement about the coefficients. We're going to leave off the A's and the B's for now. We're just going to consider the original coefficients here. So this was for our second power. And if we're trying to figure out the third power, well, first of all, the n's, there's only one way to make the a cubed, and there's only one way to make the b cubed. This 1 is going to kind of propagate down. And then the way that we made the a squared b was we took the a squared and multiplied it by b. And we took the 2ab and multiplied it by a. 1 plus 2 gave us a total of 3 a squared b's. Likewise, we had 2 ab squareds. When multiplied by b, that gave us a 2 ab squareds. And then we had a b squared that when multiplied by a gave us 1 ab squared. Those 2 plus that 1 gave us a total of 3. And so we have our coefficients for the third power. And we can run with that. Ones are always going to just propagate down. How am I going to find the second coefficient for my fourth power? 1 plus 3 tells me that this is going to be a 4. How am I going to find my third coefficient? 3 plus 3 tells me that this is going to be 6. How am I going to find my fourth? 3 plus 1 is 4. And then, like we said, 1 propagating down on the outside. How could I find my fifth power? Again, the 1s come down. This is for my fifth. What is my second term coefficient going to look like? 1 plus 4, which is 5. And then it's going to be, which is 10, and then 10, and then 5. We could go up as well, and we would see this process as well. To the first power, we would have 1a plus 1b. And to the 0th power, we would just have 1. And we could continue this process on and on and on and on and on as much as we like. It's not a particularly difficult process to do. We certainly could probably do this out to like 10 or maybe even 15 or 20. It gets pretty big, pretty not that fast. It's not too horrible, but it maybe is a little bit tedious to do over and over and over and over again. This is called Pascal's triangle. And this is another tool that we can use to kind of do these full expansions. It gives you every single coefficient basically all at once. So Pascal's triangle is exactly what we saw here, where each line represents a different power, a subsequent power, in fact, and the coefficients that would be attached to each of the terms. And it goes from left to right, term to term. So the first one is the coefficient that is attached to having all A's and no B's, and then we work our way down the triangle. So for instance, if we are trying to do the full expansion for y minus 3 to the fourth, well, this is going to be, since it's to the fourth, if I have a plus b to the fourth, this is going to be 1 times a to the fourth b to the 0 plus, this is not going to land well with where I have put my triangle. It's fine. Well, I'll shift this up actually. My triangle up here. Cool. This is going to be 1 a to the fourth b to the 0, 4 a to the third b to the 1, 6 a squared b squared, 4 a to the 1b cubed, and then 1 a to the 0 b to the 4. Now, of course, in this case, that's not our answer because we have specific values of a and b. What is a? What is b? A is y, b is -3. And so really what we get here is 1 times y to the fourth -3 to the 0. Again, you don't need to include the 1. You don't need to include the to the power of 0. I am simply doing that to make a point that we have 4 y's and 0 -3's. Plus 4 times y cubed -3 to the 1 plus 6 y squared times -3 squared plus 4 times y to the 1 times -3 cubed, and then plus 1 times y to the 0 times -3 to the 4th. We certainly could simplify this. It's not too bad, this particular one. It ends up being like y to the 4th minus 12y cubed. 9 times 6 is 54y squared. 4 times -27 should be -108. And then -3 to the power 4 is 81. And so full expansion looks more like this, but leaving it as is also perfectly acceptable. That's also totally fine. Now, is this different from what we were looking at before of like doing 4 factorial over 4 factorial, 0 factorial, a to the 4th, b to the 0 plus 4 factorial over 3 factorial, 1 factorial, a cubed, b to the 1 plus 4 factorial over 2 factorial, 2 factorial, a squared, b squared plus blah, blah, blah. No, it's the same thing. 4 factorial over 3 factorial, 1 factorial is 4. 4 factorial over 2 factorial, 2 factorial is 6. It's the exact same thing. This maybe is just a little bit cleaner to write out. So there's nothing wrong with using the binomial expansion that we have, the coefficient calculator. That is perfectly fine. And if that's what you want to do, then go for it. Run wild. That's fantastic. But we also have this tool, Pascal's triangle, a little bit more useful for when the value of n is relatively small. If I asked you to expand a plus b to the power of 50, then probably pretty unpleasant to do that with Pascal's triangle, because you would need to do 50 rows of that, and that doesn't sound very fun. But certainly doable, just maybe a little bit tedious. But regardless, we can always do the choose function, or the choose operation for all of these. And either way. Questions here? No questions, no comments, no concerns? No. Pearson might require you to. I do not. Yeah. But I don't know. WebAssign wouldn't. Not that we're still salty about that, but you know, it's fine. All right, congratulations. That is all we're doing for new content for pre-cal. Well done. Very good job. We have one more Pearson due on Sunday. We have one more quiz on Monday. And then the challenge sets would be opportunity for bringing up any of those test scores. Final day for grades, just as a heads up, I think I said that my last day was Wednesday. I just got an email. Tuesday is the last day, just because exams on Wednesday and Thursday. So Q1 officially ends on, or Q2 rather, officially ends on Tuesday. And then our exam here will be on that Thursday. But the 54 comes from doing the -3 squared to get 9, and then 9 times 6 is the 54. Okay. Yeah. But no, you don't need to simplify. All right. We will stop there.